So the equation of a sphere, and when we talk about 3 dimensions, we tend to kick over to GeoGebra. Although we don't really need to do it right now. We'll get to it in a minute. But when we write the equation of a sphere, we need to define it in terms of 2 components, 2 important components. And we'll get into, as we go forward, why these models, these equation models work the way they do. But for now, it's just a rule. All right. So sphere with center ABC and radius r can be represented by the equation x minus a squared and so on. All right. That's the standard equation of the sphere. In order to write the equation of the sphere, we need to know the center. Fortunately, we have the center here, ABC. And we also need to know the radius. All right. So when they tell us that we have a sphere that has a center of this and contains a point of that, then in order to write the equation, we got to find the distance between those 2 points. You know, because in a sphere, we're going from center out. I'll just do a quick, terrible sketch. That's all I got. That's all I can really do. So this is my center, which is why I really, really rely on GeoGebra. Because my diagrams are just so hideous. And the best I could do is maybe throw a couple of dashes on the other end to make it have some depth. A little belt. I guess, yeah, that's all I got. All right, so we got to find the length of that segment from center to point P in space. All right, so in order to do that, we use the distance formula, which is a change in x value squared plus change in y value squared plus change in z value squared. So the distance from center to the point in space, the line segment, is the radius, but we don't need to note that. The difference between 10 and -1 is 11 squared. The distance between 7 and 3, or the difference between 10 and 7 and 3, is 4 squared. The difference between 4 and -2 is 6. Difference or distance, doesn't matter, it's all the same. All right. So 121 plus 16 plus 36. So 52, 70, is it really 173? I don't even know. Yeah. So root 173. All right, so we're looking at x minus 10 squared plus y minus 7 squared plus z minus 4 squared is equal to the radius squared, which is going to be 173. All right. Now, I kind of do, as you've seen, I just do the computations off the cuff. And most of the time, well, you don't know this. I feel like most of the time I don't screw it up, but sometimes I do. It happens. And so I'd like a resource that's available that will check me. Delete it. Make sure I didn't botch the whole thing. So, no.
Does the equation equals 173 or root 173?
173, because the radius is the root of 173, but the right-hand side of the equation is r squared.
Oh, okay. Thank you.
No problem. So x minus 10 arrow over squared plus y minus 7, arrow over squared plus it doesn't have a z on the home page. When was I ever going to notice that? That's weird. Z minus 4 arrow over squared equals 173. And then it's like, what's that? That's a ring. Like part of a Q ship from Avengers. And you got to zoom out. All right, so it's a sphere. I mean, we knew it would be a sphere. If you put anything in the right form, it'll give you a sphere. It's just a question of whether it's a correct sphere. So let's plot the points. 10, 7, 4. All right, that looks like it could be the center. That's point A. Keep track of that information. -1, comma 3, comma -2. Enter. That looks like a point on the circumference, which is good. And then I just want distance. See, I accidentally hit that drop down, and now I'm paying the ultimate price. No, it's not that bad. Not that dramatic. All right, so you just never want to select anything from the drop down. It's just when you're on a touch screen, sometimes it gets in the way. So you just got to work around it. And the short answer there is just don't work on a touch screen when you're doing this. Or, go full screen, which I tend not to do when I'm demonstrating, but. So 13.15, they call that lowercase a. So I'll just take my lowercase a and square it. If it'll let me, let's see. Yeah, lowercase a squared is 173. So that means that lowercase a was the square root of 173. So I'm pretty comfortable in my work there. All right. So it takes a little doing on GeoGebra. I got this little extra business that I don't want here, but you can get your values that way. It's not unreasonable. All right. So in the second one where it says let P equal -523 and Q equal that, and PQ forms the diameter. Well, we know a radius is 1/2 the diameter. So I want to find the distance from P to Q, but then chop that in half, and that'll give me my radius. But I also need the midpoint. All right. So what I'll do here, I'll just clear all that stuff. Nah, I'm not going to save it. I'll pop in my two coordinates, -5, 2, 3. It automatically calls it A. So P, Q, A, B, whatever. I can change it to P and Q if I want to be particular about it, but I'm not that set in my ways yet. 3, 4, -1. So I need the distance. And again, I got to do it this way. Distance. Because again, I'm not selecting anything from that drop down. It only brings tragedy. All right, hit enter. Now I want it in radical form. I don't want this messy, funky decimal. So I'm just going to take that lowercase a. It called my answer lowercase a. I'm just going to take that and square it so I know what the radical is. Should be radical 84. All right, so that's what the distance is. Now I could simplify that on my own. It's basic algebra or computational skills. All right, so then midpoint. it does midpoint too, in case you're wondering. All right, so it's the geo part of GeoGebra, the geometry part. So it does all the geometry stuff too. All right. So this is all fair game. We're going to need to be able to recognize and use the distance formula as we go, but we don't need to bother ourselves with the rote computations, you know. So we're looking at 1/2 times the square root of 84. Square root of 84. I mean, if we want, we could simplify it, but it's going to be r squared anyway. So maybe we hold off on that. I don't know. And like I go back and forth on this. Every time I teach this, I do it a different way. You know, I'll just leave it this time. All right, the midpoint, -1, 3, 1. So my answer would be x plus 1 squared plus y minus 3 squared plus z minus 1 squared equals, then I got to square this guy. All right. So if I square the 1/2, it becomes a quarter. If I square the rad 84, it becomes 84. All right. So that's 21. All right. So you just do that on the fly. All right. And then you could verify by popping it in. You know, like this interface is so wonky that I think I'm gonna just not this time, but you know, you can do it, you can verify it the way we did it last time. You know, just put your equation in and make sure the original points fall. It's supposed to be on the diameter of the sphere, so make sure they fall on the circumference, and it looks like the line segment passes through the center, and you'll be in good shape. Right? So the next little section there talks about vectors in space, three-dimensional space specifically to start, but then we get into 4 dimensions and beyond. So, sorry, this is just going to bug the living daylights out of me unless I do something about it. So I'm going to do something about it. This stuff at the bottom here shouldn't be here. So we still work with the IJ notation, but this time we have a K component, right? So instead of 1, 0, and 0, 1, we now have 1, 0, 0, 0, 1, 0, and 0, 0, 1, representing 1 unit in the Z direction. Right? To represent a vector in IJK notation, it's the same idea, except again, we have that K component. So I'll just show you really quickly because it's not difficult. It doesn't take long. But for example, if you have a vector, oh, that's not too thick. Let's say a vector V is equal to 1, 2, 3. We could look at that as the sum of well, it's really a linear combination, but the sum of scalars multiplied by vectors. We'd have 1 multiplied by 1, 0, 0 plus 2 multiplied by 0, 1, 0 plus 3 multiplied by 0, 0, 1. All right. What I'm saying here is that the 1, 0, 0 is the same as saying I. So this would be like saying 1 I. The 0, 1, 0 is the same as saying J. That doesn't look much better. And the 0, 0, 1 is the same as saying K. All right. So when you put it all together, instead of having all these commas everywhere, and I'm oversimplifying it in many ways, at least in terms of the importance of it, but instead of having all these commas everywhere, you now have it written as a linear combination of the unit vectors ijk, but more importantly, it's now written as a sum rather than a list. With a sum, sums and products, we can perform algebraic operations. Like if you have like terms, you can combine them. If you want to multiply, you can multiply, things like that. But when you have it in list form, it doesn't work the same way. Right? So there is a benefit of having it in IJK notation as opposed to the component form. All right. Now, just something very, very slight. It doesn't really often come up, and it doesn't always matter. But just a little bit of the notation here, when it comes to just this guy over here, where it says vector v, v1, v2, v3, people have gotten thrown off by that in the past. We do a lot with that in linear algebra. Any vector can be written in component form where the first entry is the name of the vector subscripted with the position within the vector. So the first one is v1, the second one is v2, and the third one is v3, not because the numbers are 1, 2, and 3, but because they occupy position 1, 2, and 3. Okay? So it's very simple idea, but I figured I would make mention of that because people have struggled with that in the past. Right? So yeah. Now you can also you can denote your vectors in any way you want. Like for example, in the rules, the properties of vectors in space, and kind of change the script up here and say v is equal to x, y, z, all subbed with a 1. That's because I'm not writing it in v1, v2, v3 form. I'm writing it using the x, y, and z, because each position, each subsequent position within a vector represents a dimension. So if a vector only contained one unit, like it's a list of only one, then you'd be working in only the first dimension. 2 items or 2 elements within a vector, 2 dimensions, 3 elements, 3 dimensions, and so on. Right? When I write x, y, and z, then I'm indicating that I'm working with the x dimension, the y dimension, and the z dimension, which is the same as saying the first, second, and the third dimension. So, like going back and forth between the different forms of notation is throwing people for a loop. I don't know if there was ever a point in time where linear algebra was a prerequisite for this course, but I know there was a point where it was a co-requisite, where you needed to take it at the same time. Those days are gone, but maybe they shouldn't be, because there's a lot of things in this class where, man, if you had a little background in linear algebra, it'd be a whole lot more straightforward, but it doesn't always play out that way. So what I do is I try to give like little nuggets, little pieces of information along the way, in the hopes that you can pick up what you need related to linear algebra so that you can be successful in this course. But it doesn't always work. I try my best. If it doesn't, then let me know, and I can try to explain it more, or maybe I'll make a side video or explain it differently. Just something. Because again, it used to be a co-requisite. Now it's just like, take whatever you want. If you fail, you just take the class again. Either way, you're gonna pay, so it doesn't matter. I don't like that mentality. So anything I can do to help. Right. The rules of properties in space: scalar multiplication, vector addition, vector subtraction, vector magnitude, unit vector in the direction of v. It's all like, okay, just know these. But scalar multiplication, vector addition, vector subtraction, those are all, I think, common sense. If you really look at them, it's like, okay, if you're gonna if you're going to multiply by a scalar, as long as you know what a scalar is just the numerical value that's going to either scale up or scale down the size of the vector. Right? So like 2. If I multiply a vector by 2, I multiply each component by 2. If I'm going to add 2 vectors, I add each corresponding component. So I add the x components, the y components, and the z components. I don't cross-pollinate. Same thing with subtraction. Vector magnitude, as long as you know that the magnitude of the vector is the same geometrically as the length of the vector, then you're fine. Because that ties together with the distance formula. And all that's telling you is, oh, okay, so if I know the length of the vector, aka the distance from one point to the other on that vector, then I have the magnitude. Okay, done. The unit vector in the direction of v, all that is taking the vector and multiplying it by the scalar value of 1 over the magnitude of that vector. It's the same idea as taking each component and dividing it by the magnitude. The idea is that the resulting vector, after you perform that operation, the resulting vector itself will have a magnitude of 1, right? The purpose behind that is so that if you needed to develop a new basis for a linear system, what you can do is use that unit vector as your new basis, right? So if you think of ijk as the basis of the three-dimensional system where everything is measured in terms of 1 unit along the x-axis, y-axis, z-axis, then what if I were to say 1 unit along the 45-degree axis? I create a brand new axis, 45-degree axis, a tilt. You know, instead of wanting to go out on the x-axis, I want to go out in the general direction of the x-axis, but 40 degrees up from there, right? What would that look like? A 40 degree tilt, right? I would need to figure out a unit vector along that direction in order to redefine every coordinate in that space based off of my new unit vector in the direction of x. And then, of course, y and z in relation to that initial vector, right? Really heavy stuff because to visualize it is just insane, but it's kind of like a sphere within a sphere. If you were to kind of imagine, and this is the best analogy I can come up with, and honestly, now that I kind of said it out loud, I think maybe I'll build it one day, or at least maybe I'll come up with an animation. But if you have a sphere, and that sphere is the three-dimensional coordinate system, you know, like if you imagine you're in a planetarium, you know, you see all the stars, but instead of the stars, you know, it's not, you know, the show's not on, you know, so the stars aren't there. It's the lights are on, you know, you can see the ceiling, you can see the roof. Or if you're an X-Men fan, you're inside a Cerebro and you can see all the panels. You can see the intersection of the panels. It looks like a grid, right? So inlaid inside of that grid is another sphere, maybe a transparent one that also has its own grid that can be shifted flush with the exterior grid so that they're passing each other. So as one rotates, the other rotates. So if I decide, okay, this is my location for the x-axis, then, and I want to create a new system, then all I would do is shift up my inner sphere to a new angle, and then I would have my new x-axis coming down maybe in my direction here. Yeah. So with hand gestures, it's terrible, obviously, but I'll see what I can do in terms of coming up with an animation, because I haven't seen anything like that. I know people have different models and stuff. I know, and I've done exhaustive researches on different things that people put together for three-dimensional understanding. But this one it's so heavy that I think it would actually make a big difference in people's understandings of change of basis. You know, so yeah, I'm again making promises that I now have to deliver on. But we'll see. If anything, I can make that 3D printer purchase that I've always been intending to do. So anyway, so we have to talk about the dot product. I almost said dot product. Right? You can tell it's starting to get late in the evening when that happens. The dot product is actually a simple computation, but it's another one of those heavy concepts that it doesn't really tell the whole story when you just perform the operation until you start thinking about what a dot product tells you and what it does for you. All right. So, as we usually do, we'll worry about the how now, and we'll get into the why as we go. All right. Dot product, very simple. It's creating a linear combination between two vectors by applying a scalar multiplier of one vector upon its corresponding component within the other vector. All right. Fancy way of saying u dot v would be the same as multiplying the 3 by the -1, the 5, this highlighter's too thick, 3 by the -1, then multiplying the 5 by the 3, and the 2 by the 0, and then adding them all up. All right. We call it the dot product. Some people call it the scalar product, although it's not. A dot product and the scalar product are not always the same thing, right? It's actually kind of a mischaracterization to call it a scalar product. Just generally as a rule of thumb, if something has two names, start questioning why it has a second name. It's just good practice. Sometimes it has two different names because two different people invented it at the same time at different times and called it two different things. But most of the time, there's a practical reason why it has different names. Right? So 3 times -1, -3. 5 times 3 is 15. 2 times 0 is 0. Result would give you a 12. Right? Again, doesn't tell you the whole story. You got a value of 12 as the dot product, but in the sense of, okay, well, what on earth did that give us? That's a whole another story, which we'll get to. All right. Now, in this context, the scalar product is actually going to be the same as the dot product, but like I said, you just got to be careful about when you call something by two different names, right? So, and we'll get to instances in which the scalar product is not the dot product, so we'll cross that bridge as we go. All right. So P dot Q now this is an IJK notation, but the 10, the -4, and the 7 in component form, let me do that underneath, would be written as 10, -4, 7, and the -2, 1, and 6 would be the components of Q. So you don't really have to show that intermediate step in order to come up with your dot product. All right, so 10 times -2 plus -4 times 1 plus 7 times 6. All right, so we're looking at 18. Is that right? 22 minus 4, 18. So it's a scale. And again, it's a scalar product that is the dot product in this case because we're multiplying two vectors with equivalent dimensions. But just because you see scalar product does not always mean dot product. All right. Now, in the area below, we talk about some operations associated with the dot product. Now, these are actually incredibly important. Right? Commutative property. You would think that that goes without saying for just about everything. In this course, you're going to see that there's some instances where the commutative property, even involving multiplication, does not apply. All right, so there's that. The associative property looks kind of different from what we're used to. You know, it kind of has a little bit of a distributive property sort of feel, but then the distributive property is also there, so it kind of feels like maybe there's a little interaction between those two concepts. All right, and then the property of magnitude, which is the one I'm going to focus on right now. All right, so I'm going to put stars on numbers 3 and 4 and ask you to look at those for homework. But number 5, I'm going to tell you, I'm just going to dive right into that now, because the property of magnitude, we could actually figure that out using the magnitude formula, right? Which is to say, okay, we have B. Let's say I wanted to find the magnitude of B. What I would do is I would square each part. All right, so these are my 3 components. I would say 0 squared plus 2 squared plus 4 squared, which is going to be 0 plus 4 plus 16, which is going to give me a root 20. Let me get that in there, root 20. Which, when you simplify it, is going to give you a 2 rad 5, which is all good. Okay, but so I could say, or the magnitude of B squared is going to be the same as the dot product of B and B. So then you'll see that if we dot B against itself, and again, B is equal to 0 to 4, I'm multiplying 0 by itself, 2 by itself, and 4 by itself. I'm going to get 20 that way. That's going to be equal to the magnitude of B squared. If I want the magnitude of B, I just root that, which is 2 radical 5. All right, so then the question becomes, well, which one's better? I mean, they're both the same. They're asking you to do the same thing. It's just a question of, you know, what do you need to do with this information? All right. So if you need the dot product for something else, then, you know, the second method would be more important. The first method, not so much, but the expectation is that you know them both. All right, so let me just get rid of this title, because that title should be on the next page. The cascading effect of typos. Now, the next page is something that we'll save for next class, because that's a proof, and then we'll get into the angles. So I'll stop this video here. So this is page 13. I'm going to stop the recording. What I want